Okay, hey everyone, nice to see you guys all in here. So for today's class, we are now talking about Nelson Goodman's new riddle of induction. So we talked about Hume's problem of induction, and in the last video, I also set up kind of the background knowledge so we can further discuss Goodman's new riddle of induction. So the central question that Goodman presents in his article is how do we distinguish between what we intuitively take to be a well-behaved hypothesis and an ill-behaved hypothesis? So how do we distinguish between what we intuitively take to be like, okay, this sounds like a good hypothesis. This other one, there's something off about it. Now, to make that question crystal clear, let's compare these two hypotheses. Hypothesis 1, copper conducts electricity. So as we know, through various tests, through many tests over hundreds of years, we've come to have a lot of observational or empirical confirmation for this first hypothesis, that copper conducts electricity. Okay, now let's look at the second hypothesis, hypothesis 2. Every birthday thus far, I have turned younger than 35 years old. This is true. So every birthday thus far, here's something I've observed about the world. I've turned younger than 35. I've observed this 34 times, so year after year after year. Okay. I can even think about it in terms of days. So for so many days, 365 days times 34, I've observed that I've turned younger than 35. Therefore, the next birthday, I will likely turn younger than 35. If it helps to kind of make these two hypotheses more similar, you can think of this hypothesis written as for the past, 1,000 times, I've observed copper conduct electricity. Therefore, it is very likely that the next time I observe copper, it will conduct electricity. If you want to have the two hypotheses in the exact same type of language. Now, one of these hypotheses is well behaved or makes more sense or seems more correct than the other. And I'm hoping you're thinking that the first hypothesis, that the fact that we've observed copper conduct electricity, hundreds of thousands of times, supports this maybe idea or prediction. Let me put it as a prediction. It is very likely that copper will continue to conduct electricity. This first hypothesis seems well behaved, while the second one doesn't. Because for the second one, as you guys are all thinking, once I hit my 35th, 36th, 37th birthdays, it would no longer hold true. Whereas with this hypothesis, as we continue to observe copper conducting electricity, we just get more and more evidence for it. So it seems like we have two hypotheses, and we want to intuitively say that this first one is a good one. It's well behaved. It makes sense. And the second one, there's something weird about it. It doesn't make sense. And as we all know, part of the intuitive reason it doesn't make sense is it's not going to hold true, right? Once I hit my 35th birthday, this second hypothesis will no longer be correct. And now what Goodman asks is, well, how do we distinguish between the well-behaved or the good hypothesis, hypothesis 1, versus the bad one, hypothesis 2, the ill-behaved? Okay, that's the central question of the new riddle of induction. How do we distinguish between these two hypotheses? Now, you might be thinking just right off the bat, here's a difference between these two hypotheses. There seems to be some kind of index here, like a time index, right? Namely, like the age I'm turning. And this hypothesis doesn't have something like that. So, like, if you're thinking that, you're on the right track, like you're thinking of the right stuff. But now let's look into the new riddle of induction using Goodman's own example. Okay. So hoping you guys could see that. Okay, good. And then now let me write the other one. So this is okay, you guys can see that. Really? So this is 1. This is sorry. This is all the this is 1. This is 2. Okay. So, okay, good. You guys can see that. Okay. So now let's look at Goodman's own example, where let me now in the chat define what Grue is. So Grue is green prior to time t. Let's make that year 350, year 3000 or something. And blue otherwise. Okay, so I wrote in the chat what Grue means. I'll also write it on the board in just a moment. But here are the two competing hypotheses. So remember, inductive arguments, this is standard form. We're writing just the evidence or the reasons that support the hypothesis or the conclusion, and we draw a line to separate the two. So here's our first hypothesis, and here's the evidence. So every emerald, now just think of emeralds, every emerald we've observed thus far has been green. Therefore, hypothesis 1, it is very likely that the next emerald we observe will be green, right? That it'll also be green. It's green. Because everyone we've observed thus far as human beings have been green, and so it's very likely the next one we observe will be green. Okay? So this is our first hypothesis. And this is the hypothesis you probably all have in mind with regards to emeralds and their color. You're like, yeah, all the emeralds we observed thus far have been green, so I'm almost 100% sure that the next emerald I observe will also be green. Now let's look at this other hypothesis that Goodman comes up with. Here's the evidence. Every emerald we've observed thus far has been Grue, where Grue just means green prior to some time t and blue otherwise. So I'm going to explain that again and write it on the board in just a second. But let me first just get this out. Evidence. And every emerald we've observed thus far has been Grue. Therefore, hypothesis, it is very likely that the next emerald is Grue. Okay? Now, Grue just means, I'm going to erase this now on the board, so hopefully, just take a photo or write this in your notes. And what is Grue? Grue is just like any other color property. It just has this unique feature, okay? What Grue is just an object. Make this like a timeline. So maybe like this is what Grue is. Let's say this is a timeline. The timeline in the universe, okay? So here's us in 2025, right? And let's say this is year 3000. So this is time t. The color property of Grue is just the following. It's green prior to time t, let's say year 3000, and blue otherwise. So now here is the Grue hypothesis. Every emerald we've observed thus far has been Grue. Therefore, it is very likely that the next emerald is Grue. Notice that every emerald that we have observed thus far, given the way we're defining this new color term, Grue, has in fact been Grue. I mean, notice, right? Like we haven't reached this time t. So every emerald we've observed thus far has been green. And because of that, we can also say every emerald observed thus far has been Grue, because we haven't reached this time t where now the green emeralds switch or change colors to blue. See what I mean? So the same inductive evidence, the same observational evidence that supports the green hypothesis supports the Grue hypothesis. Because again, the Grue hypothesis is just like saying every emerald has been green up until a certain time point in the future, when at that certain time point, they will switch to blue. So every emerald we've observed thus far has been Grue, meaning every emerald we have been observed thus far has been green prior to time t and blue otherwise. Therefore, it is very likely that the next emerald we observe today, tomorrow, 2026, 2027, et cetera, will also be Grue, meaning it'll just appear green to us prior to this time index t. And I'm just making up a random year, 3000. I could have wrote 5000. I could have wrote whatever year I wanted in the distant future. Okay? Now, intuitively, of course, we all as human beings want to say that all emeralds are green, and we don't want to say that all emeralds are Grue. We don't talk about colors in this weird way where like they change, right? There's some switching. We don't think about emeralds being this type of object that looks green to us prior to some time t, and then after that time, it'll now look blue to us. That just seems totally bizarre and odd. That seems like an ill behaved or unintuitive hypothesis. In the same way, my birthday hypothesis, it doesn't seem right because there's some kind of time index. Like there's this extra thing involved in the hypothesis that implies that something will change. Okay? And so you might think, what is Goodman talking about? It's obvious that the Grue hypothesis is wrong and the green hypothesis is correct, the one that was just written on the board. But now the question is, why? Why does it seem so intuitive to us that the Grue hypothesis is incorrect and the green one feels correct? Maybe take a second to kind of think to yourself. Also, I'm sending the slides on this. You'll also have slides to kind of follow along as you follow along in this lecture video as well. So giving you guys just extra ways to kind of learn this. But when you start to ask yourself why, things do get a bit confusing, right? So let's see. This is what Goodman says. So let me quote Goodman for a second here. What Grue means is all things examined before some time index t, let's say year 3000, year 4000, whatever, some distant future time, are green and blue otherwise. That's what it means for something to be Grue. And here's a quote now from Goodman. Quote, thus, according to our definition, the prediction that all emeralds are subsequently examined will be green, and the prediction that all will be Grue are alike confirmed by evidence statements describing the same observations. So what he's saying here is the same exact evidence that we've been using to come to the hypothesis that all emeralds are green is the exact same evidence we've been using to come to the hypothesis that all emeralds are Grue, namely just the emeralds appearing the color green to us, right? Because Grue just is green prior to time t, some future point in time, and then blue otherwise. So notice inductively, we have the exact same evidence to support both the green hypothesis and the Grue hypothesis. Same evidence, same amount of evidence. Now think back to the prior video. When you have two competing hypotheses that are supported by the exact same evidence and the exact same amount of evidence, we have a rule as scientists that helps us pick which hypothesis is more likely to be true. And what was the rule? What was that assumption? Simplicity. Occam's razor, the simplicity assumption. So now let me write down the two competing hypotheses. I'm going to keep just this Grue definition up. So Grue, let me also write it down. It just means green prior to t. So t meaning time t, just some time index, and then blue otherwise. So here are our two competing hypotheses. Okay. So here are two competing hypotheses. All emeralds are green, and that's hypothesis 1. Hypothesis 2, all emeralds are Grue, where Grue just means green prior to some time index T, let's say year 3000, and then blue otherwise, meaning that all the emeralds we've been observing thus far are green, 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 green. Then once we hit year 3000, if you want to think of a even more distant future, you could think of year 5000. It doesn't matter. All those emeralds after this time index will now look blue to us. Okay, that's the Grue hypothesis. Now, as we said in the last video, scientists use an assumption. Again, it's just an assumption, but they assume that the simpler hypothesis is more likely to be true. And why is it more likely to be true? Why do we go with the simpler hypothesis? Because it makes less assumptions that require justification. And so, using that assumption again, the simplicity assumption, it seems to us, at least intuitively, that hypothesis 1 is simpler. And why? Why is it simpler? You can take a second to pause the video and think, why is it simpler? Well, because in hypothesis 1, the predicate, or like the property that the emeralds possess, greenness, is something that doesn't change. It doesn't flip. There's no flipping at year 5000 or whatever from green to blue. It stays the same. It's purely qualitative. There's no time index. There's no quantitative index involved in this property of green. It's stable. It stays the same. When we say that an emerald's green, we mean it's green now. It's in 2025. It's going to be green in year 3000. It's going to be green in year 5000. It's a stable qualitative property. It doesn't change. Grue, on the other hand, seems more complex because it is not a stable qualitative color property like green. There's a change. There's a flip, right? With Grue, maybe to make this visually crystal clear. With Grue, we have this weird flipping, right? We have, okay, all of the emeralds we're observing thus far are green, all the emeralds we've observed thus far are Grue, just meaning that all the emeralds thus far we've observed before this certain time index appeared to us green, but after year 3000, 5000, whatever year in the future, they are going to switch to blue, the color blue. Now, isn't the second hypothesis more complicated because it is invoking more claims or assumptions about color, namely that color changes, like this property of color is not purely qualitative. There's a time index involved such that it flips, right? Green flips to blue at year 5000. Doesn't that make hypothesis 2 less simple? And since it's more complicated or less simple, as we learn as scientists, we go with the simpler hypothesis. And that's why hypothesis 1 wins out. It's the well-behaved one. It's the better hypothesis than the Grue, because it's a simpler one, just as we mentioned in the last video. And you might think, okay, case closed. What's the problem, Goodman? What's the riddle? Okay. So hopefully so far so good. So you might think there we go. We just solved the solution. Why do we go with the green hypothesis? Because it's the simpler one. And as we've talked about in the last video, the simpler hypothesis is more likely to be correct because it makes less assumptions. And in this case, the less assumption being made is that color properties flip or they switch. Okay? It's purely qualitative. Now, Goodman says that you might be thinking, okay, the problem's over. We know which is the well-behaved hypothesis and which is the ill-behaved or the bad hypothesis. Based on the assumption of simplicity, hypothesis 1 is more simpler than hypothesis 2. But what Goodman will now argue is that is not the case. We cannot say that hypothesis 1 is simpler than hypothesis 2. We cannot say that. And in fact, there's no way to determine why we tend to believe hypothesis 1, the green hypothesis, and we do not tend to believe the Grue hypothesis. We have no real justified reason for that, and that's why it's a riddle. Okay, so now let's get into this. Goodman. Here's Goodman's claim. The green hypothesis about emeralds is not simpler than the Grue hypothesis. Or another way, maybe a better way of putting it is, we can't actually say justifiably that the green hypothesis, so all emeralds are green, is simpler than the Grue hypothesis, that all emeralds are Grue, meaning green prior to time t and blue otherwise. And now the question is why? Like, why, Nelson Goodman, can we not say that? So why? Well, let's think about why we think the green hypothesis is simpler. We think the green hypothesis, maybe I can write some of this in the chat. We think the green hypothesis is simpler because green is a purely qualitative, because green is something purely qualitative, and it's a color that there's no switching, right? There's no time index involved. There's no flipping from green prior to time t and then blue otherwise. And so it's like there's less assumptions being made in this hypothesis. It's like green is the stable quality, right? So why do we think the green hypothesis is simpler? Because green, so let me put it like this. Why do we think the hypothesis all emeralds are green is simpler than all emeralds are Grue? Because green is purely qualitative. There is no extra property or feature of switching from green to blue at Okay, so why do we think the hypothesis all emeralds are green is simpler than all emeralds are Grue? Because green is purely qualitative. There's no extra property or feature of switching from green to blue at time t, like how Grue is defined. Okay, so you're like, yeah, Grue is the more complicated hypothesis because the hypothesis all emeralds are Grue, what that means is all emeralds are green prior to some time t, let's say year 5,000 or something, and then blue otherwise, meaning at year 5,000 or 3,000 or whatever future year, the color of the emeralds are going to flip. They're going to now appear blue to us humans, not green to us humans anymore. That seems more complicated. That seems like it has more assumptions. Just like the case of my car, me going to the parking lot and not seeing where my car is. The alien hypothesis, the aliens took my car, is more complicated because there's more assumptions involved that require evidence. In the same way, you might think like, okay, the Grue hypothesis is more complicated because there's this further assumption about color properties that they can switch. There's more evidence needed to substantiate that. And so the green hypothesis is the simpler one and therefore the correct one and the one we should go with. Now, what Goodman says is there's an issue with this reasoning. The issue is it relies on Hume's uniformity principle. So in other words, it relies on just the brute assumption that we live in an orderly and predictable universe. Another way of just saying this is we can never actually confirm inductively that green is the more, all emeralds are green, is the simpler or more likely to be true hypothesis than all emeralds are Grue. We can't establish that inductively. We can't establish that the green hypothesis is simpler than the Grue one. Okay? And here's why. So maybe I use black here. So notice we assume all emeralds are green. So I'm just going to put green. You guys also have the slides, so that's why I'm not writing every single word down. We assume the green hypothesis, all emeralds are green. So that was hypothesis 1. Is simpler because green is a stable qualitative property with no time index. In other words, there's no switching. There's no switching at time t from green to blue. Okay, so let me make this right. So we assume the green hypothesis is simpler because green under this hypothesis is this stable property. There's no switching of colors. There's at time t, at some future time point t, from green to blue. It's this purely qualitative stable property. The emerald's green now. It'll be green in year 2027. It'll be green in year 3000. It'll be green in year 5000. It's stable. Whereas with Grue, right, the emerald is green now, but once we hit year, let's say 3000 or year 5000, it's going to switch to blue. And that seems like a more complicated property because there's the switching involved, right? There's this thing, this time index. Okay, that's why we assume all emeralds are green is the simpler hypothesis than all emeralds are Grue. But now what Goodman asks is, how do we know this? So how do we know? How do we know that green is the simpler property or predicate, I'll just use the word property, than Grue? So intuitively, we're like, yeah, it's simpler because there's no changing. Like green, we say when something's green, it's green now, it's green forever. And when something's Grue, that means it's green now, but it's going to be blue in year 5000, right? And now Goodman asks, okay, well, you're assuming that green is simpler because there's no flipping of the colors. But how do we know green is a simpler property than Grue? Like, what justification do you have? Why do you believe that all emeralds are green? And why do you not believe that all emeralds are Grue? Well, what kind of argument can you give here? Maybe take a second to pause. Like, why do you think all emeralds are green? And why do you think that it's not the case that all emeralds are Grue? Well, you're going to give some kind of inductive argument. So you're going to say, look, professor, notice that in the past, we've never observed Grue. We've never observed an emerald changing color from green to blue. So, based on all our observations thus far, based on induction, right? All the observations of emeralds we've had in the past, we assume that these emeralds will continue to remain green. We've never noticed we've never observed something like Grue, a property like Grue in the universe before. But I hope you are starting to notice what is problematic about that argument. What that argument is predicated on is the assumption of Hume's uniformity principle, that we live in an orderly and predictable universe such that the future will conform to the past. But now, when we ask ourselves, how do we really know that the future will be like the past? How do we really know that all the emeralds will remain green up until year 5000? Well, the answer is we don't. We just have to assume it. We're back to the problem of induction, which is we can't actually give a reason for why we tend to think all emeralds are green, and we tend to think that all emeralds are Grue is false. We can't really give a principled reason, because the only reason we can give is going to be some inductive type argument where we just say, well, when we look at the past, we've never seen an emerald change color, and so therefore it's unlikely that the emeralds are Grue. But now remember, Grue is green before some time t, let's say green before year 5000, and then blue after that. So all the same evidence that serves to support the green hypothesis serves to support the Grue hypothesis. The exact same evidence. And you might think, well, the Grue hypothesis is more complicated because of the switch. But the only reason why you think that is because you've never observed something like Grue before. But that doesn't mean that color doesn't work in that way. We're just assuming color works in this way. So notice, like, the first issue here is one of the reasons why we tend to think the green hypothesis is the simpler one compared to Grue is because we tend to just assume that colors are stable and they don't switch, because that's what we've observed in the past. But back to the problem of induction, we have no real reason or no real justification for believing that the future will be like the past. And so the evidence that serves to support the green hypothesis is just as good as the evidence to support the Grue hypothesis. So the evidence is not going to tell us one is better than the other. Now you might think again, okay, but again, professor, the green hypothesis is simpler because green is a purely qualitative property. There's no flip, there's no change, there's no time index involved. And remember, we just learned about the simplicity assumption. The simpler hypothesis is more likely to be true because it makes less assumptions. And now here, Goodman has a second response, okay? So Let me just erase all this, I guess. So hopefully it was. So here we go. Because we don't know for sure whether colors stay stable through time, because we can't look into the future, it's just a kind of linguistic assumption. Like, we kind of just arbitrarily decided as human beings to use this certain set of sounds to apply to this certain property that we assume to be stable and non-changing. Okay? So he's like, notice, just arbitrarily as speakers of English, this is how we define green. I'll just put green as. Oh, wait, let me actually put it like this. We define green as just a stable property. Okay, let me put it like this. But that is just arbitrary. We just arbitrarily decided to start with the stable properties of green and blue. And I just now, and Goodman just now, made up a new word, Grue, based on these pre-existing words we've had in the English language. But he's like, that's arbitrary, because now imagine counterfactually, just linguistically, we decided to start with the words Grue and Bleen. So let's say, again, Grue is green prior to time t and blue otherwise. And Bleen, let's say we have this other word Bleen. So again, imagine just we're going back in history, and instead of starting with the words green and blue that we just randomly, arbitrarily decided to use as English speakers, we instead decided to start with these words instead. Where Grue is green prior to time t and blue otherwise, and Bleen is blue. Okay. Let me actually make the graph. Okay. So here we have the words Grue and Bleen. And notice we're defining them with relation to the words green and blue. But now what Goodman says is, suppose instead of starting with green and blue as the random arbitrary words we picked to refer to these color properties, what if instead we started with Grue and Bleen? Like, we just decided to define color in that way instead. Notice, like, whichever we pick is arbitrary, because it's not like Grue is the more likely to be true color property than green, because all the observations we made thus far of emeralds being green is the same justification of emeralds being Grue. So he says, now imagine instead of defining Grue and Bleen, Bleen is now blue prior to time t and green otherwise. Instead of defining these two new words we made up with reference to these words we've already had, let's imagine the history of linguistics is a little bit different. And we actually started with the words Grue and Bleen, and we're now defining green and blue with regards to Grue and Bleen. So now how would that look? Now green would be, let's say, I'll just do green. Green now in our new language, where we're starting with the words Grue and Bleen, would be this, right? It would be Grue prior to time t and mean otherwise. Okay. Now here's the timeline. Time t could be any time index, your 3,000, your 5,000, whatever. And now this is how we define green. Okay, so let me now make this point crystal clear, because it's important. As English speakers, we have started with the words blue and green to describe certain colors. And it's arbitrary what words we pick and how we come to describe these color properties. It's arbitrary that we came up with green and blue as the words to point to the objects in the world like grass and the sky, and we didn't pick some other words. And also notice the same evidence that supports the idea that the grass is green or emeralds are green, that same inductive evidence supports that they're Grue. So it really is arbitrary that we use the word green instead of Grue. And now what Goodman is illustrating to us is, imagine for whatever reason as English speakers, we decided to use the words Grue and Bleen. Those were the words we began with, because for whatever reason we involved the time index in the way we define color. And it's not because it's and notice it's not more complicated, because all the evidence thus far inductively support this idea that color could be something that can change at a certain point in time. Okay, so we could have just as easily started with the words Grue and Bleen as English speakers, and then defined green, this new word we're coming up with regards to Grue and Bleen. Where now green is just Grue prior to time t and Bleen otherwise, meaning that, like, look, it just stays green. So it's like it's Grue prior to time t, where Grue is like it's green up until year 5,000, and then Bleen otherwise, where Bleen is like it's green post time t, right? So post year 5,000, it still remains green. So it's the stable green that we come to think of. We could have started with Grue and Bleen and defined green in terms of these terms. Okay. Now what he's trying to illustrate here is, like, you might still be thinking that the green hypothesis is simpler because there's something linguistically simpler about the predicate or the word or the property green, because it's stable and there's no switching. But we can't, first of all, we have no evidence to support that idea, because again, we don't know that actually, like, we don't know that green is a stable property. For all we know, everything is Grue. Like, everything that appears to us that is green is in fact Grue, and it's going to switch at year 5,000. So there's no real evidence or argument we can give as to why green is like, you know, it's observationally it's a simpler property. And then next he says, also, like, you might think, okay, well, linguistically green seems like a simpler word or a simpler property because it's just assumed to be something stable with no changes. But he says that's just as arbitrary, because deciding green as the word we're going to use to refer to things that are green, like grass and emeralds, and assuming it to be something stable, that was just an assumption, an arbitrary assumption we just made linguistically as English speakers. We could have just as easily started with the words Grue and Bleen and defined this new word that I just made up in 2025 called green in terms of Grue and Bleen, just Grue prior to t and Bleen otherwise. Okay, so green prior to t and green post t. So here what Goodman's saying is, Even linguistically, green is not a simpler predicate. It's not a simpler property than Grue and Bleen. So we assume it to be, but there's no evidence to support that. And even linguistically, there's no reason to believe that green is a simpler property or a simpler word or term or predicate. And so once you start to notice this, these are like now the two prongs of the argument. First is like the inductive part, and now this is the language part. Once you start to notice this, you really can't say that all emeralds are Grue is the more complicated hypothesis compared to all emeralds are green. Okay? And here's an example he gives to make this again clear. It would be like saying this, okay? This is the linguistic point, okay? I guess I'll just use the curve. Okay, here are two sentences. All grass is green. I don't know, I'm using green. I should have thought of a different word, but whatever. And all grass inside California and outside California is green. This example is meant to illustrate how Grue is not linguistically more complex than green. To say that Grue is linguistically more complex than green is to say that somehow this second sentence is more linguistically complex than the first. But now notice these two sentences are logically equivalent. They point to the exact same things in the universe, right? They mean the exact same thing. That's what I mean by logically equivalent. They're both true in all cases. There's never going to be a case where this is going to be true and this is going to be false. Never, right? And so, all grass is green. This sentence, linguistically, logically, is just as simple as all grass inside and outside California is green. They're saying the exact same things. They're pointing to all the things in the world that we refer to as grass, and they're saying that that thing is green. It's just in the second sentence, we have a spatial index, right? Inside and outside California. But the meaning of these two sentences isn't different. It's not like if I told you all grass inside and outside California is green, you would like disagree with me and say, no, all grass is green. What are you talking about? You could never disagree with me because these two things mean the exact same thing. They're logically equivalent. If this is true, this has to be true. They both have to be true or they both have to be false. They're logically equivalent. And so in the same way, when we say all emeralds are, in the same way, that we start arbitrarily with the words green and blue and then define Grue in terms of green and blue, we could have just as easily started with these words Grue and Bleen and defined this new word green with regards to those words. And once you start to notice that, you start to notice that we can't even say that green is somehow linguistically a simpler concept than Grue. It's not. It would be like saying this sentence is somehow simpler than this one. How could that be? Their meaning is exactly the same. Okay? And so this is now the end of the article. He's like, you might think that the Grue hypothesis is more complex linguistically, but that is fallacious. It'd be the reasoning you would use to assume the Grue hypothesis is linguistically or language-based more complex would be the same type of reasoning you would use to say that this sentence is somehow logically more complex than this. But that makes no sense because these two sentences, although they're using different words, there's different scribbles here on the board, they mean the exact same thing. They mean the exact same thing. Okay? And so that is now the new riddle of induction. I know this is the long one, so I'm going to just end it here because you guys have the notes and the slides. So the new riddle of induction just is, how do we differentiate between what we tend to think is a well-behaved versus ill-behaved hypothesis? Like, on what grounds do we think all emeralds are green is a good hypothesis and all emeralds are Grue is not a good hypothesis? You might think the green hypothesis is simpler because there's no time index. But the only reason why you think that is based on induction. And again, the problem of induction tells us that we don't know for sure that the future will be like the past. So for all we know, it could be true that all emeralds are Grue and they will change color. They will flip from green to blue in year 5,000. Next, you might think, well, just the word green is simpler. The word green is a simpler word because there's no like time index involved. There's no flipping. There, Goodman says, that's just arbitrary. We just arbitrary linguistically decided to start with the words green and blue and now make up these new words, Grue and Bleen, Grue, and define Grue in terms of green and blue. But we could have just as easily as English speakers and just as arbitrarily started with the words Grue and Bleen and defined green in terms of Grue and Bleen. And once you notice that linguistically, the word green is not simpler. It's not a simpler property than Grue. It would be like saying somehow this first sentence is simpler than the second. But that makes no sense because these two sentences written on the board, yeah, one has more words, but the meanings are the same. They both point to the exact same things in the universe, the grass, and they're calling it green. Whether I say all grass is green or all grass inside California and outside California is green, it doesn't matter. I'm saying the exact same thing. If one person says this and one person says this, it's not like they're agreeing. They're in total agreement. They're stating the exact same fact. And so the second point of Goodman's argument is, even linguistically, we can't say that green is a simpler property or a simpler term than Grue. And now that is the new riddle. We really don't know how to distinguish between, or we really have no justifiable argument or reason to say that the hypothesis, all emeralds are green, is more likely to be true or is better or is simpler than the hypothesis, all emeralds are Grue. And isn't that strange? Because intuitively, we all want to say all emeralds are green, and we don't want to say that all emeralds are Grue. So that is the new riddle, and I am also sending the slides. Thank you, everyone, and I'll see you soon.